So, hello everyone. I'm Andra, and today we'll be talking about large-scale graph processing using Apache Flink. First of all, I'd like you to interact as much as possible. So this was meant to be a tutorial initially, so we'll do some coding in the middle of it. Have fun. Okay, so let's see what's Jelly. Jelly, as you may have heard in the introductory section, is Flink's large-scale graph processing API. It's built on top of Flink's Java API, and right now we also support Scala. Jelly was officially released in Flink 09. It contains several off-the-shelf library methods that can be used by simply calling the run method from the graph instance. And it also supports both record and graph analysis in the same application, simply because it's built on top of the Java API in Flink. Also, we leverage Flink's efficient delta iterations to support various iterative algorithms, as we will see in the following slides. So where is Jelly on the Flink stack? Well, we're right on top of the Java API, very high level. We're also on top of the Scala API now. Let's see how we could use Jelly. First of all, it's good to know that in Jelly, a graph is represented by a dataset of vertices and a dataset of edges. And we could create a graph afterwards from a dataset, from a tuple dataset, or from a collection, let's say from an array list. How do we do that? Let's check out an example. Here I have read the edges from CSV. First of all, then I use graph from dataset and the dataset of edges. I don't give away the dataset of vertices here, but what Jelly does is that it automatically deduces these values from the edge values. Also, I'd like to initialize the vertex values with infinity. That's why I use this map function here. And finally, I pass out the execution environment. Are there questions up until here? Is it clear, or? The same would happen from a tuple dataset, but then you don't have a dataset of edges. You have a dataset of tuple 3s and tuple 2s, respectively, if you want to pass the vertices. And from graph from collection, you would have an array list instead of a dataset. Let's move forward and see what kind of properties you can extract using Jelly. You can extract the dataset of vertices, the dataset of edges, the vertex IDs, the edge IDs. Also, you can get a dataset of tuples, vertex ID in degree, vertex ID out degree, and vertex ID degree. Finally, you can extract the total number of vertices and the total number of edges from the graph. And a function I personally like is get triplets. This function allows you to switch the computation from vertex-centric to edge-centric. And how that works is that it actually returns a triplet of the source vertex and its value, the target vertex and its value, and also the payload. Afterwards, you can use a map function. Yeah.
About the triplets.
Yes.
Is it also in the optimizer that it figures out when it's for the user good that it is distributed by edges or by vertices? Or
no, actually you have to figure out from your algorithm if it's better for you to retrieve these values or not. For example, if you want to weigh the graph with some distance, say your vertices are points in a plan, then you could use this to retrieve the vertex values and weigh the edge. Then you have all of them. You have the edge weight, and you have the vertex values. So it depends on the algorithm whether you need to use this or not.
So if you know the algorithm, you could say, okay, I want, that makes more sense.
Yeah.
Okay. So it's not possible to get that through the optimizer?
No. Up until now, no, but it's a good suggestion. Also, we can transform the graph similarly to what Flink does in its dataset, but for graphs. We do map functions. We have two map functions, map vertices and map edges, respectively. And what these do is that they receive a map function as a parameter, and they apply it to the vertices in the graph and to the edges. We also have filter functions. We can filter on vertices, on edges, or subgraph, which does filtering on both the edge dataset and the vertex dataset. How we do that is we simply pass filter functions to these filter on vertices and filter on edges. And to look at an example, Say we have this input graph, and we would like to do filter on vertices on it, firstly. And the filter function is vertex get ID greater than 2. So as you can see, we just remove the vertices 1 and 2. Of course, if we remove 1 and 2, we cannot have the edges, because they would be purposeless. So we remain with this subgraph. And if we do filter on edges, on the other hand, with the filter function edgeGetTarget equals to 4, then what happens is that we keep only the edges that point to 4, and all of the others are deleted. For join transformations, we have 4 kinds of functions: join with vertices, join with edges on source, and join with edges on target. And what happens here, for example, I will explain join with vertices. Say we have a data set of vertices, and we would like to apply a map function only on a subgraph, not on the entire graph. So what we do is that we join with vertices and give it a data set of tuple2s and a map function. And what this does is that it joins the vertex ID with this key from the tuple2 and applies the map function. Similarly for join with edges, but this time this key gets joined with the source, and this key gets joined with the target. Join with edges on source and on target, just do the same as join with vertices, only on the source target, on the source or on the target of the edge. If we would like to reverse the graph, we can do so with jelly. This simply switches the direction of the edges. And also in jelly, a graph is by default directed. So if we would like to perform operations on an undirected graph, we use the getUndirected function.
I have a question to that. Is it possible to give also join hints, like doing the edges are really small also?
I have a proposal for that on the Flink mailing list. It's not accepted yet, but maybe we can overload these functions to actually receive join hints as well. So to have let's say a boolean somewhere saying, okay, I want to pass join hints, and then it would go to the other function. Very nice idea. Also in jelly, you can do this union operation and also a difference. The union operation takes 2 graphs as parameters and yields a graph that has the common vertices and edges of the 2 graphs. If a vertex appears once, it will be yielded once. But if an edge appears, if a vertex appears twice, it will be yielded once. But if an edge appears in both of the graphs, it will be yielded both times. Also, we have a difference method, as I said, that takes 2 graphs as input and simply leaves out the common parts. For graph mutations, as you may imagine, if you want to modify a graph, for now you can add vertices or add a single vertex, add edges or add a single edge, or simply remove a vertex or an edge, etc.
So are these mutation methods, are they triggering a kind of Flink job every time?
Yes, so they are actually creating a new graph.
Okay.
So when you add a vertex, you take the old graph, you add this new vertex to it, and you return a new graph. It's like super internal information. You don't care you're in an API. Okay, so reduce the neighborhood methods. This allows you to perform an aggregation on the first hop neighborhood of a graph, of a vertex in the graph. And it's always easier to find out how it works with an example. So I prepared one for reduce on neighbors. And let's say you have this input graph, and you would like to apply reduce on neighbors with a compute minimum function and with edge direction out, let's say. So what this function does is that it looks at the out neighbors of each vertex. So for 3, it looks at 5, 4, and 9. And it picks the minimum. In this case, it's 4. But actually, 4 does not improve 3. It's not lower than 3. So 3 keeps its value. Then we go to 9, and its neighbor is 4. And we see that 4 is lower than 9. It improves 9, so we change it to 4. Can someone tell me what happens for 5? because it's too quiet. So 5 looks at its out neighbors. It's trying to choose the minimum. Okay. It's 4, okay. But why is it 4? It looks at its out neighbors, it finds that 4 is the minimum, and 4 improves 5's value. Okay, awesome. Thanks. And 7 hasn't got any out neighbors, so it keeps its previous value. Yes?
What would happen if 7 would be 1?
If 7 would be 1, then 4 would look at its out neighbors.
Well,
1 is
4, but for 9.
for 9.
9 before or 9
It's only on the first hop neighborhood of the graph.
Okay,
So it doesn't see, 9 doesn't see 7.
Well, but if you process 4 before 9, then 4 would reduce to 1, and then 9 would also reduce to 1. So is it deterministic or non-deterministic?
That's actually a good question. So I would say, but I have to check, I think it's non-deterministic. So if it happens that 4 processes 7 before and then 9 comes to process it, it may happen that you get a different result. But I have to check, so. So right now I showed you 2 functions that work for commutative and associative operations, so I was choosing the minimum there. But if you would like to use a more complicated function, then you have to switch to group reduce on neighbors and group reduce on edges, which actually receive the same kind of parameters, just apply different operations and behind to support bigger variation of functions. Yes?
What's the direction? So if it's a directed graph, it should follow the normal direction, right? So it doesn't mean that we can follow the opposite direction?
If it's an undirected graph,
It follows the normal direction, right?
if it's undirected, it has edges in both directions, and I think it doesn't matter whether you pass it as in or out at that point. So, can you repeat the question? So you have an undirected graph, and
It's like different questions. First of all, what's the direction? If it's just following the normal direction of directed graph?
you have to pass the direction. So you're asking whether if you have a directed graph, if it will follow the normal direction or not. You have to still pass the direction. I mean, that's the way the...
There's an option to do it the opposite.
Yes, there's an option to do it. So if you pass edge direction in, actually 4 will look at 4, 3, and 4 in this case. 4 will look at 9, 3, and 5 in this case. Yeah. Okay. We also give the opportunity to validate a graph. So let's say in many cases, for me it happened, you may mingle with your input data set and remove a vertex or an edge in between. And you would like to make sure that the graph is the one you expect, so you use a validator for that. In this case, we would like to make sure that the edge IDs correspond to the vertex IDs. So what we actually do is that we call graph.validate with invalid vertex IDs validator, which in this case will yield false because you don't have the 6 vertex ID from the edges in the vertices dataset. Okay? Yes?
So can you also generate a graph only from edges?
Yes. But you would need to generate a graph from vertices and from edges and from vertices if you want to pass vertex values to the graph. That's mandatory. Because then, so from dataset with only edges passed, will give you vertices with their IDs only, and you could pass an initial value for all of them, let's say infinity, which cannot pass an initial value from, let's say 1 has 2, 2 has 3, etc. That's why you would need to read the vertices as well. Other questions? Okay. Now the fun part. We support 2 types of iterations, 2 iterative models in Jelly. We support the Prego model and a slightly modified version of Power Graph's gather, apply, scatter model. We just have the gather, sum, and apply, the first two steps, as we will see in the following slides. So for Pregel, what we do is that we have two UDFs. We tell the vertex, firstly, what kind of messages it's supposed to pass, and when it receives messages, what kind of update should it make based on those messages. So what the vertex does is that first it receives messages from its neighbors. Based on those messages, it updates its value, and if the value was updated, and only if, then it sends the new value to the neighbors. So let's see how this works on an example. The single source shortest paths. What this does is that it takes a source vertex, in my case it's 1. This has distance to itself 0, sorry. And it would like to find out the distance to all the other vertices in the graph, the shortest path. So what it does is that it adds up to the value of 1, it adds up the edge value and sends it to the out neighbors. So 1 will send 0 plus 2 to 2, 0 plus 3 to 3, 0 plus 4 to 4. Then 3 will send infinity plus 2 to 4, 2 will send infinity plus 1 to 4. And in this case, well, 2 has to choose. Which one do I like best? Which one is the minimum, infinity or 2? Of course it's 2, and it updates its value to 2. Same happens for 3, infinity versus 3. 3 is better, so I choose 3. And for 4, we have to choose between 4, infinity, infinity, and infinity. The best is 4, and we update the value to 4. What happened here? Well, 2 changed its value, 3 changed its value, and 4 did. But 1 didn't. So 1 doesn't participate in the computation anymore. In the second yes?
Question. So if you would imagine another level, doesn't matter.
What kind of level?
Like another node, and
Yes.
After 4. And
Okay.
But 4, I would imagine if you update when infinity stays infinity.
If you have another value, another node coming from
After 4.
after 4.
Yeah.
Yes. So if you have 4 and then I don't know 5 here, 4 will send infinity and
Infinity plus infinity
is infinity.
Is it a change value or isn't it?
I think I don't know about infinity though. Yeah, it should change the value. But yeah. Yeah. Okay. So in the second super step, we have 2 that changed this value, 3 that changed this value, and 4 of course, but 4 doesn't have out neighbors, so we leave it out of the computation. 2 will send 2 plus 1 to 4, 3 will send 3 plus 2 to 4. 1 doesn't send anything anymore. So 4 has to choose now. Its previous value was 4, and it received 3 and 5. Oh, look, 3 is smaller than 4, so I will choose 3 and update my value. And right now, 2 didn't update its value anymore, 3 didn't, and 4 doesn't updated its value, but doesn't have any out neighbors, so it cannot send to anyone anymore. In this case, we would get the result yielded here. And I'd like you to remember this result, because we will go to some coding a bit. You'll see that I kind of did a bit of work for you here. I initialized the source vertex value to 0, and the other vertices have infinity as a value, as we were in the initial state. And now I would like you to help me write the vertex update function and the messaging function based on what we had in the example. So in the vertex update, which one do you want to start with, vertex update or messaging? Doesn't really matter.
Are you implementing now what you just showed?
Yeah, the single source shortest path algorithm. I didn't explain any other one, so it would be complicated. Okay, so what should we do next? We have here a vertex, which is the current vertex that we're looking at, and we have an iterator that goes through all of the messages that vertex received. So what could we do? We saw that We saw in the example that the vertex looked at the values and chose the minimum. So
do we need to know which superstep we are, or?
absolutely not. I mean, for this one, the superstep executes the same kind of functions. So you don't care in which superstep you are.
But the first step I don't sum.
In both of the steps, the vertex sends its value and the value on the edge to its neighbors, plus the value on the edge.
Okay, so when do I sum in the update vertex or in the send message?
Very good. Who said that? Have some more view. Okay, so in the send message, you sum up the vertex value with the edge value. So, okay, if you already gave away the messaging function. So what we do is that we go through all of our...
We can't see it.
Can you scroll?
Oh,
We don't see it.
sorry. Do you see it now? That's as low as I can go. Ah, wait a sec. Yep, awesome. How low can you go, IntelliJ? Let's see. Then you have to go through all of your out neighbors, right? So what you do is that you make a for, and the edges of k and double, in this case. The key can be of any kind, that's why it's a generic. Then you do from edge to the entire set of edges, which in this case is get edges. It's a function that does it for you. And what you do here is that you send a message to the edge target. And what does the message contain? Well, it actually contains the vertex value plus the edge value. Great. So then, if you...
mean that there are two targets?
What is an edge of one target?
That's another edge, if there are two targets. So if you have a vertex 1, 2, and if you have 1, 2, and 1, 3, that's two edges.
There are multiple vertices.
Okay. So what happens in the vertex update?
You iterate.
Awesomeness. It's like they're all saying, you iterate. Okay. So you iterate. Let's say you have a double, and this is the message, and it goes through all of the in messages. And then,
Compute the min.
okay, so if message actually improves my min distance, then I will make min distance, equal to message. And finally, so this just looked at the out neighbors, I still have to look at my vertex value. So does this set of messages, this computed minimum from the set of messages, improve my vertex value? I have to check that. So if vertex, it's called here, dot get value is actually higher than this minimum distance that I just computed, then I will set the new vertex value to the minimum distance. And hopefully,
Don't I need to take the minimum of all messages?
but you do.
That says the computing is a for before.
So you receive,
You can initialize min distance with vertex and value, right?
what?
You can initialize min distance.
Yeah, because the processing.
So, say you initialize min distance with vertex gets its value.
Okay. So if we go to running this now, I need the full IntelliJ to run it, sorry. If I go to example and then do single source shortest paths, let's click run. So if we look at the example, oh, you cannot see the result. Okay. Okay. So we will see that we actually got the correct result. If you don't believe me, then 1 had 0, and 2 got 2, and 4 got 3 in the end, and 3 got 3. So the result is the correct one, or the expected one. Let's see now. This is the code snippet that actually shows the code that we saw. We now move to gather sum apply iterations. So for those of you who know Powergraph does gather sum apply and scatter. In Flink, we only support one update at a time in the delta iterations, so we can only support the 2 gather sum apply steps. And since the majority of algorithms update the vertices, we chose to support these 3 UDFs: a gather function, a sum function, and an apply function. So what happens here, as opposed to the vertex update and the messaging function, is that a vertex gathers information from all of its neighbors first, then sums up that information or applies an aggregator on it, and afterwards it applies the information it learned to its vertex value. So if we go back to the single source shortest path example, the gathering will actually receive neighbor values plus their edge weight. The sum, or accumulate in this case, will choose the minimum out of the values it received. And in apply, we take this minimum that we just computed and we compare it with our actual value. And if the minimum improves our value, we update. If not, we just discard it. So let's see again on the famous example. What happens here is that in parallel, so as opposed to Pregel, this gather step happens in parallel and gather sum apply. 1 sends 0 plus 2 to 2, 0 plus 4 to 4, and 0 plus 3 to 3. Then 2 sends infinity plus 1, 3 sends infinity plus 2. And what happens is that in the sum step, we just look at the received values. So in this case, 2 will choose 2 as a minimum, 3 will choose 3, and 4 will look at its received values. 4, infinity, infinity, chooses 4 again. In the apply step, we now look at what we had before, what was our previous value, and what's the newly received minimum. And if the minimum updates our value, as happens in all the cases, then we change the vertex value. In the second super step, we send the newly updated value to our out neighbors. We don't send the neighbors gather, sorry. And 4 will gather 2 plus 1 and 3 plus 2. And we'll see that 3 is an improved value for it. It will choose 3 out of 3 and 5. And then it will look at its previous value. So it had 4, and now it received 3. So it will update its value to 3. And the result is, as expected, the same. Are there any questions here? Okay. Now if we go back to the code, let's make this a bit smaller. And also I need this version and the presentation mode. Great. So again, we see that we have an initialization step where we say that the source vertex gets 0 and the other vertices get infinity as a value initially. And then we have to write these 3, wait a sec. Yep. Then we have to write these 3 UDFs. A gather step, a sum step, and an apply step. So again, I would like to ask for your help. What could happen in the gather step? So keep in mind that here you don't iterate through the neighbors. You get a value from the neighbor each time. So you have a neighbor as a parameter, and what would happen? Come on, I know you know. So it's a one-liner. It's actually super easy. So What them?
Both documents, neighbor, the value and the edge value.
Awesome. So we have neighbor dot get edge value plus neighbor dot get neighbor value. Awesome. We now move to the sum. We have graduated. So in the sum you have, you now gathered the values from the neighbors, you computed the minimum from there, and you would like to see if this minimum, no, actually you have not computed the minimum yet, so you just got a bunch of edge values plus the vertex values. So what do you do with them in the aggregation part? You guys are not allowed to answer anymore. Okay, you choose the minimum, and that's a math.min of the new value and the current value. What happens in the apply step? So you have, you now have a summed value of the neighbors, and you have your old distance. So you would like to see whether it improves it or not.
You use an if and compare?
No way. Okay, so you look at your old distance, and actually you look at if min distance, sorry, if new distance is called here, is lower than your old distance, then guess what? You update the value. So that would be set result to new distance. And now, if we do run, okay, let's go to example and then to, then I wish me luck because I have to do a right click with 2 fingers. Perfect. I'm a pro now. Okay. It's not obvious yet. So we again have 2 with value 2, 1 with value 0, 4 with value 3, and 3 with value 3, as in the previous case. Are there any questions? Okay. So what was the main difference between, I have a question then if no one else has. What was the main difference between the vertex-centric Pregel model and the gather sum apply model? So why one and not the other? I'm pretty curious. Why should we need 2 of them?
You could decide what to
Yeah, but maybe in some cases one would be better than the other, or what was the difference actually? Because there was a slight difference there when I showed the graph. Yes?
Maybe we can optimize the second variant because the for loop is done by the framework.
Yes.
And in the Pregel model we have the for loop in our UDF. Flink didn't know about it.
Actually, this gather step happens in parallel as I showed here. So instead of having one message at a time, you have all 3 of them and you process them. So yes. That's one of the advantages. Okay, you've seen this, actually this is what we implemented. So as I was saying, some of you may argue, okay, but this vertex-centric and gather sum apply, they're kind of the same thing, right? You can say the messaging function is a gather plus sum and the update is an apply. Why not? Well, because this gather sum apply happens in parallel, as he observed, and this is best for skewed graphs. So let's say you have a vertex with a lot of neighbors, and what happens is that at some point you process neighbors faster using this method rather than the vertex-centric method. Another argument, which is a bit internal, is that vertex-centric uses 2 cogroups, whereas gather sum apply uses join, map, reduce, and another join. So basically, for commutative and associative combined functions, it's always better to use gather sum apply, because it can make use of these combiners that reduce uses in the background and speed up computation. But the problem is, of course, there's a downside, because otherwise we would just use gather, sum, apply. This GSA iteration only gathers from immediate neighbors. So you cannot say, okay, send to vertex with ID 7 in gather, sum, apply. Whereas in Vertex-centric you can do so. So for this subset of algorithms, it's not even recommended, it's a must, because gather, sum, apply doesn't support it. We have to use the Vertex-centric iterations. So, is it clear until now? Or? Okay. What we have in the library of algorithms is a set of already constructed methods, a weakly connected components algorithm, also a gather, sum, apply version of it, a community detection algorithm that detects communities for our given graph, a PageRank algorithm, and also a gather, sum, apply version of it, single source shortest paths that you've already seen, with a gather, sum, apply version of it, of course, and label propagation. So now I would like to move to an actual use case example. So let's say we have Jelly, we understood what it looks like, and we would like to use it for something. So we have a Spotify playlist, and we have as input a set of user ID, song ID, and the number of times it was played, triplets. And also we have a set of bad records. So the user tells us, okay, I really don't want to listen to this set of songs. And then what we do is that we first try to filter out the bad records. The code is not so important, so I'll just explain it like this. We get the triplets data set, we get the mismatches, and then we do a co-group of the triplets with the mismatches on the song ID. And we see that if the iterator of invalid songs doesn't contain any element, then this is a valid triplet and we collect it. This is basically done using a regular Flink co-group. Then we would like to see what are the top songs for a user. So we would like to create something like a graph out of this. Let's say the source vertex is the user, the target vertex is the song, and the edge value is the number of plays that that song had for this particular user. So what we do here is that we create a graph from the valid triplets, and we use group reduce on edges to compute the top song for each user. And of course the edge direction is out because you want to look at the songs and not the users. What happens in the get top songs per user is that you iterate through the edges and you do a max play count. So you look if the edge value, which in this case is, as you can see, the number of plays. So if the edge value is greater than play count, you update play count. And the top song is the target of that edge. Then you return a tuple of the vertex ID, which is the user, and the top song for that user. I guess it's pretty straightforward. Okay. For the next step, we would like to cluster similar users together, so to create a user-user graph based on the common songs that the users are playing. So in this case, we would again use Flink. We would group by so create a user-user similarity graph. We would group by the song, and then we reduce. We do a reduce group, which basically iterates through the edges and adds the source to a list, and then it creates pairs of the user and the other user, basically. So it looks at the songs and looks at the users that played that song, have that song as a most listened to song, and actually forms pairs of these two users. And then you do a graph from data set to actually get this final graph. Finally, so to cluster these similar users together, you use this label propagation algorithm that I previously said that we have already in the library. So what you do is that you update the vertex values with the, you randomly assign an initial ID, an initial label, because the label propagation algorithm needs that every vertex has an initial value to it. And afterwards, you run this label propagation algorithm to see which users are similar to a certain amount. Okay? So what we have next is actually the Jelly blog post and the Scala API, which have already been published. I would like you to check the Jelly blog post. It's been published some days ago. And also the Scala API should be checked out because there were a lot of people asking for it. We are planning to add more library methods, of course, and there's ongoing work in Stockholm on integrating Jelly with Flink streaming. Also, we are planning to come up with some graph partitioning techniques. This particularly is my thesis, my master thesis, so I'm working on introducing a set of operators that work for highly skewed graphs when gather sum apply fails, for example. And we also would like to provide bipartite graph support. There are many other things, but you should check them in the Jelly roadmap. So this is the end of the presentation. If you have questions that you didn't ask here, we could talk about them, or you could mail us at the user and dev Flink mailing lists. Questions? Okay. Either everything's clear or nothing is. Okay. Yes.
Okay, I'm not very much into graph processing.
Me neither. Okay.
How high is the communication overhead for various operations? So you showed some operations where you send messages from one vertex to the other. What if my graph is super huge and distributed over lots of nodes? How does the optimizer deal?
Wow. I need Stefan for that. Some Flink guys telling me. So the question is, what does the optimizer do if you have a lot of machines and a lot of vertices? Right?
Yeah.
Yeah, so the messages are basically usually just hash partition. So whenever you do a distributed operation, I guess most of the operations will be operating on partition data sets. So the data set is partitioned and you just need to shuffle the messages of the network. So the good thing is if you do like something like these product style operations or some type, if you implement your algorithm, this framework, these basically...
I can say this. It basically happens that once your vertex value does not get updated anymore, it doesn't participate in the next super step. So once you advance in the computation, you lose the vertices until you don't have vertices anymore. So even if you start with a big graph, as we proceed with the iteration, we get less and less vertices.
So under the hood, it does not do any message passing. Under the hood, only stuff is joins, home groups, users, etc. So it's the regular Flink execution engine. It does not have a graph. The execution engine does not have a graph processing mode. It's only the API on top that it tricks you into thinking
that you're processing graphs.
But under the hood, it's just the regular joins.
Yes.
So did you also do some tests on real-world data?
Yes. So what kind of tests are you talking about?
Like running the algorithms, for example, from the library?
Yes. So all of the algorithms in the library are actually tested on at least the Twitter follower graph. Okay. And the sample of the Twitter follower graph, yes. And we also test on Orkut and Friendster from Snap.
Have you tested with Frank series benchmarks?
You don't want to hear the answer to that. I mean, imagine that he outruled, what was it, Power Graph and all the other super graph processing systems. So the thing is... Yes, definitely. It's super slower, like 5 orders of magnitude. It's yes. So actually, if you super optimize the algorithm to work on a single node, and if your data set fits into the main memory of your laptop, you shouldn't actually be using that parallel data flow system, whatever. You should keep it on your laptop. So if everything works on your laptop and you have enough memory, it's definitely better to use the laptop. So it's like trying to screw a screw with a hammer. So you're basically, yeah. In that case, it doesn't really make sense. Yes? Other questions? Okay.